Okay, so yeah, so it's kind of a very broad topic, right? Because a lot of things, everything we're doing has some footprint into QCD, and then how we're actually looking at it with electron scattering. So today's kind of goal is to kind of get us all on even footing, right? And then we can, tomorrow, we'll kind of jump off that and get a little more detailed into some of the different experiments and measurements. Okay, so the course overview, some of this you kind of already covered probably, but maybe not in as much detail last week. So we're going to talk about elastic scattering, quasi-elastic scattering, and deep inelastic scattering. Okay, so we have our plan, right? So we're going to like learn all about the nucleus. And the reality of it is that it's never quite as clear as you think it's going to be when you start out. So it's kind of always like that too when you're in grad school, right? Like if everything worked the way your advisor told you it would work the day that you started your plan, I think it would be very different, right? Okay, so once we kind of establish ourselves here, then we'll be talking specifically more about hadrons in the nucleus. And so, and those, hints and signatures of QCD and how they manifest and where we're going experimentally to understand that. Okay, so what are we trying to learn about? This is like the elevator pitch that somebody asks you when you go home and they're saying, what are you doing in graduate school, right? And you have to explain to them, well, there's like these quarks in the nucleon, and then they're doing stuff, and there's like virtual particles. And really, we're just trying to understand the strong force, right? But the reason we want to understand the strong force is because if there was some way to really understand, the details down here, we would like to be able to understand things like neutron stars and astrophysical type phenomenon. And then you could always even branch off into, different topics, like are there hints from, dark matter and things like that, because, we don't know what matter is structured like, but we know what it's structured like here in the standard model. Okay, so we're going to kind of start from nothing to everything. So we have sort of like our islands. So we have, the vacuum where you have these exotic mesons and baryons. And then we have our quarks and gluons, degrees of freedom. We have few body dynamics with protons, neutrons, and nuclei. And then eventually we want to extrapolate that stuff to, heavy nuclei. So we're talking like neutron stars. And, the question is how do we kind of build that bridge from one island to the next? How do we connect all of those pictures to really make a complete understanding of the nucleus without just using some models and assumptions in one region and some models and assumptions in another region and never trying to understand how they connect? Okay, so when we're talking about the nucleus, we're talking about a collection of bound protons and neutrons. And when we're talking about nucleons, we're talking about them as a collection of bound quarks. And so this whole story of nuclear dynamics is the story of systems and interactions, right? So we have the nuclear interaction arises from quark interactions. So we know that it's kind of, a very messy picture where you have protons and neutrons, and there's like this residual interaction that gives us the strong force binding the nucleus. And then you have, of course, other types of interactions, like you have nuclear in medium effects, which affects these quark distributions. So we have, old Ben over here. Oh, wait, he's talking about a different force. So it's an interaction created by quarks and gluons, right? And then it binds the nucleus together. So how do we explain that? And that's what our goal is. So some of the relevant quantities, a very famous example for, for the atom and the nucleus is that you have this clock face, right? And you can study it and you can make all these notes about how, what the period is and how, it's ticking and it does this and that. And you're trying to describe these mechanics without seeing them, right? So we can't just like open up and easily see things, but that's kind of what electron scattering lets us do. So we still have to have some models and ideas to make smart kind of predictions. So we can actually sort of, tease out like how the gears work. And so some of the tools, some of the actual things that we extract anyways, when we study in electron-nucleus interactions, we want to understand, right, the shape. So we can look at nucleon structure. We can look at the charge distributions. So these are the form factors, which we'll get more into that. So anybody from at least from Hall B or from SBS is probably interested to hear about the form factors. We can talk about the nucleon momentum distributions, clustering correlations, we can talk about the nuclear force as it arises from quark interactions, right? So that's very important. And then we can make comparisons between the quark structure of bound and free nucleons. So you've probably heard everybody talking about this EMC effect, and you've, thought about that. So that's, we'll talk a little bit about what that implies. And then you can also, then there's like kind of newer things that people are starting to look at now, which are really interesting. You can look at, the gravitational density of gluons. So there's some gravitational form factors. And then, to all of these things, you have to understand the basic dynamics of what it is that you're doing. So when you knock a proton out of the nucleus, for example, it's not always going to come out. Sometimes some of it's deflected or absorbed and it doesn't survive. And so then you have transparency, or if you smash up your proton and you knock out a quark, it hadronizes, right? We don't see free quarks. So these are all things that we want to understand, and these are some of the the quantities that we'll kind of try to examine. So so electron scattering, we view it as the nuclear microscope. So we can, the really good things about it, right, is that the electron's probe-like, it's point-like, so it has no structure. So and it samples basically the whole nuclear volume. So you can kind of tune the kinematics of what it is that you're looking at to determine what it is that you want to measure. The electromagnetic interactions are really well described by QED. So of course, for everybody who loves Griffiths and Maxwell, those are very good descriptions, right? And we learn those because then we can apply those to other, to these diagrams, but we can also apply what's similar, right? That's like our fundamental basis for when we jump off and start trying to learn about QCD. So the interaction is weak. And the theory works. So we typically use the first Born approximation, which I'll talk about in single photon exchange. So in this case, for most considerations, you can just worry about the fact that the probe interacts once, and it can probe, and you can probe the entire nuclear volume. So that's a big advantage. The downside, of course, to electrons is that the cross sections are small, so we need high rate, high duty machines. So that's what JLab does. And then of course electrons radiate, which complicates things. But we can, we can handle that. We just have to study it. So the underlying premise with electron scattering is that it's really just all photons. So the electron interacts with the nucleus by exchanging a single virtual photon. So you can have a real photon, for example, that can excite something in the nucleus and it de-excites and we can see what comes out. Or you can have your incident electron, which emits this virtual photon, and that can interact with the nucleon that you're concerned about. And so I guess I should pause here and just say that if there's any questions, like while I'm talking, just raise your hand. So we'll try to cover them along the way. Okay, so so then we basically define this this photon in terms of its energy, and we call it like the energy and momentum transfer of the reaction, right? So you have Q and you have nu, sometimes omega. I tried to keep them the same, but you might find a few instances of omega. And so the interaction with the virtual photon with the proton depends strongly on this wavelength, right? So this is like what defines our spatial resolution and what it is that we're looking at. So we have really big wavelength, very low electron energies, then we're basically looking at like a point-like object, which the proton is not, but we know that now because we can start to increase electron energies. And so when you have low electron energies, you can start to see that the scattering equivalent of that is like equivalent to that coming off of an extended charge object. So not a point-like, but that there's some like swimming around of charges in this distribution, right? And then you can have high electron energies where you start to actually scatter off of the individual quarks, and you can resolve the substructure and momentum distributions of those quarks. And then at very, very high energies, of course, the proton, we can start to probe different types of quarks. You got valence quarks, C quarks, and you can start to kind of understand that picture. So this is generic inclusive. So we say inclusive scattering at a fixed momentum transfer. So again, this is our nu. So this is our E beam minus our E prime. And this would be like our cross section versus as a function of the momentum transfer, the energy transfer. And so you can look here anyways. So we'll start with, we can start with the nucleus, right? So you can scatter off of the whole nucleus, right? So that would be like a Q squared over 2A, the whole nucleus. And you can say something then about the size of the nucleus and, you know, the charge components of the nucleus and, you know, the skin and things like that. Then you kind of start to increase your momentum, your energy transfer, and you can start to get to basically where you haven't quite knocked it out yet. So you can get a giant resonance here. You haven't quite knocked it out yet. But then you have your quasi-elastic peak. So this is where we spend a lot of time. These are things that they're bound, and we can knock them out, kind of making a quasi-free type of assumption. So we still haven't broken them apart. We haven't shattered them. So once you start shattering stuff or exciting stuff, then you end up in this regime. So this is where you excite maybe a proton or something to a delta or n-star resonance. And then you have the deep and elastic scattering regime where you can start to scatter off of this, basically you shatter stuff apart and then look what comes out. And so you can do the same thing off the proton itself, right? And then we make comparisons between what's going on in the nucleus and what's going on in just the proton by itself. And so here, you know, you have the elastic peak, which is kind of just like a delta function. So you're just scattering off of the proton. Then you can excite it, right? And then you can have deep and elastic scattering where you're scattering off of quarks in the proton, for example. So we're going to come back to that, but that's like the EMC regime. So EMC effect is how basically like a proton is different inside of a bound nucleus versus a free nucleus. Okay, we'll talk more about it in detail, but that's the EMC effect, and you'll hear people talk about it. But it's named for their collaboration. So we'll talk more in detail about that probably in the afternoon or later this afternoon. Okay, so different kinematics can teach us different things, right? So just kind of at the opposite ends of the spectrum, like I said, you have elastic scattering. So the nucleon initial and final state, I mean, it's still intact, right? So you can scatter an electron, virtual photon off the nucleon. So this is, say, a proton that, let's say you knocked out the proton. So now you're just going to measure the proton and learn things about it. Deep and elastic scattering, maybe you're scattering and you scatter off a quark, or you're basically breaking up the proton, and then you're looking at all the stuff that comes out of it. So deep and elastic scattering is, you know, if you're playing pool, you're going to ruin somebody's balls on the table because you're going to break them. Right, so these are the three regions that we're going to talk about today. So we have elastic, quasi-elastic, and then this deep and elastic regime, and we'll talk about the EMC effect. Okay, so the idea is that we're kind of looking at different, we're looking at the nucleus, but we're looking at it in different ways, right? So in elastic, like I said, we can learn about nuclear structure, charge radius, neutron radius, electromagnetic form factors, and charge distributions. And you think about it as like the whole nucleus, right? You can't really resolve quarks here. They matter, but we can't really resolve them in this picture. So then as you increase Q squared, right, you have you can start to interact and discern nucleons, so to speak. So yeah. So then you have the quasi-elastic, which is the momentum distribution, shell structure. So this is where we'll talk about the shell model for the nucleus. And then we'll talk about the deep and elastic scattering, which I've kind of already mentioned, but we're basically scattering off of quarks is how we can think of it. Okay, so form factors are similar to the diffraction of plane waves in optics, which is something that we all learn as we're becoming physicists, right? So we can rewrite basically the scattering of the electron in a static potential due to an extended charge distribution, like as shown here, right? So if this circle was, let's say, some sphere of charge distribution contained, right? Then we can describe the potential at some distance from the center given here, right? Where the integral of this charge distribution, let's just normalize it to 1. Okay, so we can use first order perturbation theory to calculate the matrix element, right? And so we can use Fermi's golden rule. We can we can take the perturbing potential with the initial and final states, and we can rewrite the integral as shown here. And so then we can take our potential from the previous slide, because this is due to charge distribution of charges as shown here. And we can basically start to evaluate our integral. Okay, and then of course, the reason for doing all of this is because, you know, the Born approximation, you guys can laugh, maybe missed it. Okay, so the Born approximation allows us basically to write the potential as like a Fourier transform to obtain the amplitude, and the amplitude, you know, the scattering amplitude squared gives us the the cross section, right? So we can fix this R prime, which is basically to every single point within the sphere, right? Because it has some size. And we can make a substitution over here, and voila, I've done the work for you. So you can say that this is equivalent to scattering from a point-like object times this form factor, right? Okay, and so this is really useful because the form factor basically then contains all of the information of this distribution of charge in this extended object. And so, it's just the Fourier transform of the charge distribution is shown down here. Okay, so we didn't talk about it yet, but if you recall that the Mach cross-section is sort of like just scattering from a point-like object, right? It doesn't have any information about this being an extended object or anything. We ignore target recoil, and it's relativistic. Okay, so then we can rewrite the Mach cross-section in terms of the Mach cross-section multiplied times this form factor, okay? And so basically we have some finite scattering center, and the plane waves are getting dispersed, essentially phase shifted by interacting at every point in space of this extended object. And so that's what we can describe here. And so shown along the top is basically like our density function. And so if you consider that it's point-like, then the form factor is just 1. Okay, so that's why, well, we'll come back to that. So if it's exponential, then you can say it kind of behaves as a dipole. So this is a good description that we use a lot of times to make comparisons to, how the proton's different from a dipole. And then there's, other different functions, right? So this is just the Fourier transform of the distribution. So again, we can kind of go back to this idea. Let's talk about physics of what we are measuring in electron scattering here. So we have this sphere, 3D sphere, radius A. And so let's say it has a uniform charge distribution, some rho. And so then you can say that the charge, which would normally be like, you would think of just summing all the number of protons or something, would be the volume times A cubed of this times the charge density. So then you can perform basically the form factor, the Fourier transform here, and you can basically evaluate, if you work through all the math, you can get down to the bottom to something of this form. So again, this is normalized to 1, so that that's why we have 1 over z at the front. It could be anything. So this form is interesting because the numerator, as you see, has an oscillatory type of behavior. So you could plug this into anything on your computer right now, like put it into Excel or into one of your little Mathematica programs, and you would see kind of, it's just oscillating. But then it falls off as this 1 over q squared at small scattering angles. And so basically, so this is like a real cross section of calcium-40 and calcium-48 that was measured. And you can basically see this oscillatory type of behavior, right? And it's falling off as you go out in scattering angle degrees. So pretty simple kind of assumption here that you can do to get the general form of what it is that you're measuring on the right. Okay, and I think you've probably seen maybe these pictures too, because these are really nice. So nuclei, basically what we've learned is that nuclei we can kind of approximate, right, as a spherical ball of fixed density. And so the general size of the nucleus scales as a to the 1/3. And the radii are approximately 1 Fermi times a to the 1/3. And so we can write basically precise, we've shown through scattering experiments that the form factor has an approximate dipole form. You can see it as the one up here, which is sort of the approximation that we've worked through to get here. But you can also, we'll come back, maybe some of you are more familiar with the form factor GD 1 plus, Q squared over 0.71. So anyways, these are the same, they're just different units. And so anyways, so these were a bunch of Saclay measurements mostly. And so what you see basically on the x-axis is kind of this, this R. And you would see basically the density function along the vertical axis. And you can see how, the bigger nuclei kind of push further out in R and, have this, they all have kind of like this similar type of form, giving us just a general good idea that we can kind of approximate things as a spherical ball. Okay, but up till now, we've kind of ignored the recoiling proton when we're talking about things. So let's talk about lab frame kinematics, right? So we have an electron comes in and emits virtual photon on, let's say, a proton over here, and then scatters, right? And so we detect things like the scattered electron, because that tells us a lot about the kinematics that we're looking at. And then we can also choose or not choose to detect the scattered proton. And so we can construct some invariants here. So we have the Q squared, which is shown down here. So the 4 momentum transfer squared, or we have the invariant center of mass energy of the system. So these are all things that we can use to make determinations into the kinematics that we're going to use in the experiment for what it is that we're going to study, right? So this is showing, and this is showing here, as you see, this would be kind of like scattering from a stationary object, right? A stationary proton, and then the proton scatters. Okay, and then, but we know that the proton has some finite size, right? So, so we can think of, there's different components of that. And so, you can write the cross section in terms of Rutherford scattering. You can include the proton recoil factor, which is basically the scattered E prime over E, the incident electron energy. And then you can include this electromagnetic scattering factor. So if you were to move this over here, right, you get the Mott cross section. And then you have the magnetic term due to spin particles. So, but the proton is not point-like. And so we account for basically the finite size of the proton by using 2 structure functions. And so we can use the charge distribution as described by GE. So again, it's like a Fourier transform of the density, the charge density distribution. And the magnetic moment distribution is described by GM. So then you can kind of expand things and write things in this nice way down here, as you can see from coming up here. You can write in the Rosenbluth formula, where basically you can see this term at the front. So you have Rutherford, proton recoil, then you have your GE and GM in terms of the angles, right? Okay, so recall the form of the Mott cross section, just because on this slide I ended up just I didn't write it out. So there's a few different ways we can write the cross section in elastic scattering. Okay, so we can write it as in terms of F1 and F2 structure functions, or sorry, form factors. And these are basically linear combinations that you can make to get to the Sachs form factor. So that conversion's down here at the bottom. So you have F1 and F2, which is what they kind of started with when they were describing, this extended object. And then for many reasons, it was better to switch to sort of a GE-GM definition because of like minimization of errors and other types of things that we learn about the form factors. Okay, so you can see that these are written in terms of F1 and F2. And so there's this tau and this kappa. Kappa is the anomalous magnetic moment, and tau is your Q squared over 4m squared. Okay, and then we'll talk about this probably later this afternoon again, but you can also rewrite this in terms of the longitudinal and transverse response functions. Any questions? Okay, we'll talk about what those mean, but basically we can measure, we can look at how the virtual photon polarization is basically received by the proton. Okay, so if we rewrite the cross section then as shown up here, and we sort of simplify everything. So we have GE squared and GM squared. We have this tau. And so we have this factor out in front, which includes the Mott cross section and the proton recoil. Then experimentally, what we can do is we can do what's called a Rosenbluth separation technique. And so you can take basically a bunch, so you fix your Q squared, right? Because Q squared, you know what your electron coming in is, and you can fix like where you're looking for your scattered electrons. So you can fix Q squared, and then you can study the angular dependence of the cross section. So we write the reduced cross section over here. So we just divide by this guy. So you just write this reduced cross section. And then you can see here, it's sort of like what is it, like a times x plus b, right? So it's just a linear line almost. And so then you come down here and you can say, so we can take a bunch of measurements in terms of your x, which is this tan squared theta over 2. And the intercept then will be this term, and your slope will be determined by GM. So this is a very popular technique for getting at a lot of the form factors. I guess some of the drawbacks of this is that it requires, you'll have to correct for, there's certain nuclear corrections that you'll have to include. We can talk about those. And I guess we'll lead up to that. So from elastic scattering on the proton, we can determine the dipole form factor. So I gave you this earlier. We already kind of know we use this form. So we just sort of divide through everything, right? And look at how GEP, so this would be off the proton, the electric form factor off of the proton, and the magnetic form factor off the proton relative to GD. And so we can look at the deviations. So this is a lot of global data, all different over the years. GEP was for a while kind of looking like it was at 1. And, GM has sort of this other type of distribution. And so this is all from Rosenbluth separation data, but that's not the complete story. So, right, so you can look at the, basically the helicity amplitude of the single photon exchange has an increased asymmetry for double spin asymmetries. What does that mean? So we take a longitudinally polarized beam, so we know what the polarization is of your electron coming in, and then you can either scatter off of a polarized target, or you can scatter off an unpolarized target and measure the polarization, the recoil polarization of the proton. And so these have an enhanced sensitivity, a different sensitivity to the form factors. And so you can write the transverse and the longitudinal components that you would measure of this recoiling particle. And you would basically, what you can measure really, really well is the ratio of GE to GM. And so that's what's kind of shown here. And so this increases your sensitivity to GE for large Q squared because GE dominates at small Q squared. And it also increases your sensitivity for GM at the small Q squared where it dominates at large Q squared. So it just, so this is kind of like a preferred, much higher sensitivity method. And I think the surprising result was that in a series of polarization transfer type of experiences, right, where you have GE over GM over here on the vertical axis, this is all that data I was showing you on the other page, the Rosenbluth data. With very high precision, it comes down. And at some point, it'll probably also cross 0. We haven't measured that yet, but it's interesting. And so, initially everybody was kind of like shocked. So I sort of put this crater up here of this, this guy, he was pedaling his bike on this straight line, not a straight line. He hit kind of his ditch. So he has to understand something now because the data doesn't just happen as somebody tells you, you expect it to happen. And so basically there was a large discrepancy between the Rosenbluth data and the polarization transfer measurements. And a lot of this has been explained in the context of the 2 photon exchange corrections. So as we kind of talked about, we were talking about everything in terms of the single photon exchange. And, but you are sensitive to the two photon exchange and you'd have to correct this data for that, which would actually bring it down. And then, right, and then there's kind of a significant dependence on the radiative corrections. And so that's why it's important, that we kind of go back. There's a whole program now in at least 2 of the halls that are trying to understand that better. So the implications of this is that perturbative QCD predicts that there would be a plateau, right? So for this F2 relation to F1 form factors with respect to Q squared. And so this is kind of, so what we're showing here on the left, right, is we have GE over GM. And then on the right, as I showed you, you could rewrite GE and GM in terms of the F1 and F2. And so they expect basically a scaling, so like a plateau here. And it's basically with the polarization data, it's still climbing. And so that could have all sorts of different explanations that people are excited to talk about. And we'll kind of touch more on this a bit later. But it's just interesting, I think, to keep in the back of your mind that it's not plateauing with the data. Yeah, okay. So I was going to talk about I was just going to briefly touch on some of the experiments here at the lab, because I know there's at least a few students that are part of the SBS program, but then there's also a class 12 experimental program that's also looking at least GMN, right? So shown down here on the bottom left, you can measure GMN. They use a ratio method where they scatter off of deuterium and you measure your EE prime N and EE prime P, okay? And they can basically do this ratio method to kind of extract the GMN form factor. And so the reason this program is important, right, is because you see these red dots here. These are kind of the sensitivities that we would expect from this Hall A SBS program. And so you can see that they're kind of pushing all the way out in much higher Q squared than we have before. So we're going to get a better picture. Anyways, so this is for the neutron, so the magnetic moment inside the neutron, right? So even though the neutron has no charge, it's overall charge neutral, but right, these are hints of QCD, right? Because it's made up of quarks which have charge. Okay, and then you have neutron on bottom right here. So you have GE N over GMN. And so these are extracted, again, talking about this polarization transfer of observables. So you can do either, so the first part of the experiment basically does scattering on a polarized target. And the second part of the experiment will run a different type of, well, they'll just measure the recoil polarization. So they'll just, all they care about is that they have a longitudinally polarized electron beam, and they'll just measure the polarization transfer to the scattered nucleon. Okay, so that's where they will measure some of these points. So that's interesting because they'll use both methods, and they should trace out basically this line as shown here. Okay, so then there's GE over GM for the proton. So you can also measure that. And so again, they're just measuring the polarization transfer using, for the proton in this case, with a longitudinally polarized electron beam. And this will be on proton target, right? Okay, and then class 12 also is probing this GMN out to pretty high Q squared over here. Okay, and so these things are also interesting because we're still on the topic of nucleon structure. And so to measure the proton charge radius, we use the fact that basically as Q squared goes to 0, the charge radius then becomes proportional to the slope of this GE. Okay, so you could rewrite the GE form factor in terms of this expansion with the expectation value of the radius of this distribution. And so then you can say that the radius of the proton, then you're looking at this slope as Q squared goes to 0, because you can't actually measure it at Q squared equals 0, because there's nothing to measure then. So this is interesting, and this was a big program for the lab for a while, and there's even an extension still planned for the proton radius, because there was kind of a high contention in different measurements, because you can use elastic EP scattering to determine GE, right? Or they were also looking at the radius of the proton by replacing hydrogen with basically muonic hydrogen. So you take the electron out, you put the muon in, it has a smaller Bohr radius, and it's much heavier than an electron. So basically it's more sensitive to the radius of the proton because it spends more time going into the proton, essentially. Yeah. So we were talking earlier, we were talking about the one with all the plots was like the radius of like nuclei, right? So here we're just talking about, it's the same thing, but it's basically, we're just talking about it for the proton itself. So how do we measure just what the radius is of the proton? So this is just related to GE. And so again, that's why we go to this small limit as Q squared goes to 0, because we don't want any contributions from GM. We just want to be sensitive to the electric part of the form factor. Yeah, that's kind of how that's how we use it. So this was a pretty high impact experiment for the lab. This was in Hall B a few years ago, and then they just recently published the results. So they measured GE for the proton as a function of Q squared. And this was a really important measurement because they did it at small angle and small q squared. And so that way that would limit some of the issues with the extrapolation getting to basically a q squared of 0, right? And so, so what's shown here is that they had some ideas that basically, and they were able to show this, that depending on kind of some of the previous experiments that were done and some of the fitting extractions that they did, that you can kind of, you can put a pretty big moment arm on your fit to move what the proton radius actually is. And so, so they did a very conservative fit and were able to show that these higher order polynomials that other experiments were using, predicts a higher proton radius. Okay, so then we look on the right here, so you can see the data. So this is the proton charge radius. And so you have this band here, which came, a lot of it's from EP scattering. And then you have basically the line here, which comes from very highly precise. You can see the really precise muonic hydrogen spectroscopy experiments. And you can see where this new recent result. So it still has larger errors, but it's much closer to the result of the muonic hydrogen. So it's starting to close that gap. So there's still kind of a lot of people that are working on this to try to understand the previous results, right? Is this just a fitting problem? Is it, a normalization kind of problem? And so I think it'll be a while before everybody's in agreement, but it was interesting anyways that this result tried to reduce a lot of the issues and assumptions that you had to make in other experiments, and came up with a smaller proton charge radius. So again, we were talking about the form factors, but now we can go back to the charge densities, right? So we can think of, so this is just the vertical axis is this charge density, and the x-axis is like your distance from the center point. And so you can say, so what's really interesting anyway, so, this is kind of intuitive, right? The proton peaks at low values and then has this long positive tail, which they can kind of explain with, this charged pion cloud that kind of draws out some charge. Okay, but the neutron is really interesting, right? Because it's negative, and then it goes positive, and then it's kind of got this long tail again. It's a little hard to see on this plot where it is above 0. So the part above 0, you can think of as when the neutron is fluctuating into sort of like this proton with a pi minus, right? And so that gives you like this positive charge density here, and then sort of this pion cloud tail again, which brings it down. And then, but then at the very small center, the negative part is really interesting. And this is kind of a good indication because the neutron's made up of 2 down quarks, which are negatively charged, right? So in this way, you can think of that the location of the neutron. So if you go to like the high momentum limit, you can think that basically the quark that's carrying the most momentum, which will, statistically speaking, be a down quark, so a negative quark, would define where the neutron is. And so this would sort of dominate. This is why you sort of end up with this negative charge distribution on the low end. If that makes sense. It's really interesting to think about, actually. So this is a good hint anyways of, this idea that QCD is playing into all of these things, even though we're not talking about quarks and gluons, but there's just sort of signatures of it everywhere. And then, some people, even just take, then they can also define like a charge radius for the neutron. Okay, so for an elastic scattering summary, basically we can measure things like the charge and magnetic moment distributions of the nucleons. These are described in terms of the form factors, which, yeah. Mm-hmm.
So you mean to say that the twin down quarks and the neutron would be independent?
Yeah, probably. So in the high momentum limit, so as you're getting closer and closer to like where the center is of this neutron, it's going to be dominated mostly by the down quarks. Yeah, okay. So these are kind of just the broad ideas that we get out of elastic scattering. We use form factors. We can extract things like the radius and structure. And this tells us about, the structure of nucleons and nuclei. And we know that nucleons aren't point-like. So that's obvious, but it's interesting because we're seeing kind of signature and hints of it in scattering where we're not necessarily looking for quarks, right? We're just seeing the result of them. So I can either pause here or, yeah, okay.
So let's
Okay.
think, because we are gonna have a break.
Yeah, that's fine, that's fine. I'm fine, that's a good stopping. Yeah, are there any other questions?
I have one question.
Yeah,
So if you go to slide 30, can you explain?
30?
The
Okay,
experiment, how they measure, like one of the experiment, how they measure the charge radius?
yeah, so because this is electric form factor on the proton, they're basically measuring just it's just a high precision EP elastic scattering. And so, so if I go back to, let's ignore this formula for a bit, come back. Well, okay, I guess we can stay here. So let me go back. I want GM because you can see, it's a little hard to see in the equations, I think. Okay, so we're talking about small angle, okay, and we're talking about small q squared. And so in that limit, GM sort of just becomes like a statistical uncertainty. Like it's no longer really like driving it. So they kind of calculate what that contribution might be based on different models, and they say that that's like, they just take it as a systematic. And so they basically measured high, like EP elastic scattering cross section, and they use Muller EE scattering to kind of normalize everything and to understand, to understand the efficiencies in the experiment.
If you extract G and then relate it to the formula to get the radius.
Right, so they kind of use this expansion you can think of, right? So they're trying to get the slope as q squared goes to 0. And so basically, if you take the slope of this as it goes to 0, this is where you start, you can almost give this plot to anybody and say, okay, fit this data and tell me what you get as the slope goes to 0, right? And so then you have to make some educated ideas about how you do the approximation and the fitting. But that's why they did a pretty thorough idea of the fitting, because, well, first of all, if you haven't met Doug Higginbotham here at the lab, he's very passionate about this topic. And so he was able to show that he could take other data because they were fitting it with high order polynomials, and he was able to show that if you float normalizations differently, that you could get a different charge radius, right? And so so they were doing kind of a very careful job in trying to minimize the amount of extrapolation they had to do.
Why there's two specific bands?
Why there's 2 bands? So there's like review articles written on this topic, but it depends who you ask, right? But I think the general consensus here at the lab is that some of these measurements there's a lot of work that has to go into the normalizations because of where they took the data, and they have to smartly extrapolate, right? If you're fitting your data with high order polynomials don't always do well when you're extrapolating outside of them. And so that's why there's people that have taken, even at this lab, they've taken global data like this and gone back. They gave it to high school students and went back and were able to fit it and show that they could get this or they could get this. Why it falls into one of those 2 camps, I'm not exactly sure about that. But they were able to show anyways that like there was basically kind of some, maybe some not so great on the scientific side of really ruling out every possibility. So that's why these measurements are considered much more precise, because you look at the error bars on these. So these are, a little bit better. But then again, there's been other spectroscopy experiments that still measured high. So this is a contention thing, right? This is like people still go to conferences and there's still heated discussion about it. I encourage you, if you have questions about the experiment, because this is a nice Nature paper. So Nature is always nice because it's kind of written for everybody. So you can look that up too. Any other questions?
We don't have any questions. Let's have about 15 minutes break now before the next lecture.
We have one more.